All right, so we got lab day. The conclusion that we're trying to reach, the claim that we want to report is mu, coefficient of friction. It's always between surfaces. All right, and so we're going to test a wooden surface, a wooden plank, and a wooden block. All right. So the coefficient of friction, wood on wood, right? That's the claim that we're going to from this data here. Hopefully everybody had a chance to take a look at the video where we calculate the same quantity mu for measuring the critical angle. Bonus lab will be able to follow up with that. Hopefully, with this bad collection. The mass of this block is 250 grams, so that's 0.25 kilograms. All right, so make sure when you do this lab that you're using a physics block. Otherwise it might not work. So we have 250 grams and putting a kilogram of mass on top of that. So there's 1 kilogram of matter inside of this object. So that's an amount of matter, right? Mass is an amount of matter. Here on Earth, there's an influence on that mass, right? The influence of gravity. So weight, the force due to gravity, is mass times the acceleration due to gravity. It's the same second law of motion, we just calculate weight. So A is local g, and the mass to begin with, 1.25 kilograms. Everybody with a calculator knows that 1.25 kilograms of mass on Earth weighs what's it weigh? Unmute your mic. There we go. Hold on. Let me check the chat. The board is on Instagram. On Instagram? It should be, but sometimes we get really bad reception. I did have a meeting this morning, so kind of rushing the chalkboards up to speed. Well, we're at Equinox +1 today. We're 1 day past Equinox here in September. Stand by. There we go. All right, it should be updated now. No reception back there. This is all right, so what number do I write here? Who's got it? 12.26. how many newtons of normal force is the board exerting back up on the block? (12.26 newtons. This is actually what we're going to plot on the x-axis, okay? The normal force, because theory suggests, I mean, this is a fun lab. Force of friction equals mu times the normal force. Right? Fun. Force. It costs me 2 newtons of force to pull that block along. But once I exerted the 2 newtons of force initially, I kind of talked through this before. But as soon as I apply 2 newtons of force, it should be an object in motion remaining in motion. Like I exerted a force on it, I changed it, velocity from 0 to some non-zero value, but it comes to rest. So an object in motion remains in motion until or unless an outside force acts upon it. The outside force is friction. And so that's really what we're measuring. Pulling along the constant velocity, yeah, I'm directly measuring my pull force. So I can understand through the second law of motion that what I'm indirectly measuring is the friction acting against it. So there's also kind of see how that, I mean, just imagine a very, very rough set of surfaces. That means that the coefficient of friction mu is going to be very high. All right. So if we have something with a certain normal force, 12.26 newtons, the weight of that block right there, and the coefficient of friction were 1, at a value of 1, that would mean there's the same amount of friction as there is in its weight. That's not the case here, right? Like I can pull it along with much less force than its weight. We already kind of know, well, the coefficient of friction wood on wood is less than 1. Well, less than 1. We can just kind of take a quick ratio and go, friction divided by normal force, this number divided by this number, kind of gives us an idea about the coefficient of friction. But we wouldn't want to like use that single data point to reach it. Better to vary the weight, keep measuring the friction, and kind of see how well this holds, right? That will establish a trend, and we can find the best, the slope of the best fit line representing the trend in that data for each. But if the coefficient of friction were 1, like if it were a lot harder to pull that along, okay? You need to supply just as much force, which equals the friction, as its weight. What if it were greater than 1? What if we're like 2? So I had something that weighs 12.26 newtons, but it costs like 24 newtons of pull force to pull it along. What could we say about those surfaces? Yeah, they're very rough, they're very sticky. What might you say to that person that's pulling along this block on these rough surfaces? Have to exert twice the force of the object's weight. Yeah, pick it up, right? It'd be easier to pick it up and carry it than to try to pull it along. So some surfaces are so rough that we got to, a little bit too far now. All right, let's back over here. What we do on lab day? Very independent variables. The independent variable today is the normal force. We're varying. There it is. That's 1 kilo, 0.25 total kilos. Everybody with a calculator knows has a weight of 22.07. Normal force, 22.07. Frictional force. Hypothesis. A quick calculation of 2 divided by 12.26 gives us an idea about 1.16 for the coefficient of friction. Now, if I say, I kind of have an idea about that, I know the normal force here is 22.07. I'm going to expect a frictional force of about 3.6. My calculation is 4. So you can start to get an idea about what you might expect in the dependent variable. Now this instrument is sensitive to the Newton. I mean, you can try to use it, so it's kind of going to be two, but it's graduated sort of the lines are very close to each other. I'm going to call it 5 there. I mean, I can kind of use my judgment and say it looks like it's a little bit under 5, but it's certainly not on 4. You know, like I said, well, I'll call 4.5. That's up to you as a scientist. It's like collecting data and you kind of know your instruments. You're like, yeah, I feel better about making a judgment call that's in between these two. Remember, we capture the precision of our measurements with these certainties. So we kind of dealt with last week. We're not really worrying about it. You know, once you kind of get going with this lab, the data comes out. So we got 2 data points. I'll go ahead and publish the data once we've collected it all. For right now, let's vary this 1.5 kilograms now. I'm going to vary the independent variable 1.5 kilograms. So that odd is let's vary it out each time. That's better. I don't care how much you can vary by. I'm going to vary by 1.5 kilos. There. Now the math is way tougher. 3.75? Check that. Y'all check that. 3.75 kilograms of mass here on Earth weighs 367 grams to 9. This would be nice and 7, 8. 36.79 newtons of normal force. But how much frictional force would act against it if I were to float along at constant velocity? That's what we're all dying to know. Newtons. 7 newtons of pull force, 7 newtons of frictional force. Those forces in the x direction are balanced. Let's open up the request line. How much do we want to vary the independent variable by? Get our 4th data point today. What's the liking of the in-person students? You want to like jump down at this last data point? Or you're saying let's just increase a whole bunch right now. Like I got more weights out there. Now let's use this as an opportunity to sort of think about what would give us better results. I mean, should we try, like I was saying, vary the independent variable over the greatest range possible? So like, well, let's keep adding weight to it and let's get, really high values here. This can measure up to 50 of full force. So maybe it would be better to kind of get an idea about, well, how much full force would be required. So let's do this. 1 kilo, 3.5 kilograms. Okay? Now we've just added 3.5 kilos to these 3.75 are already there. Seven point two five, right? 7.25 kilograms. There's an equivalence that you should be mindful of as a student of physics. It's true here on Earth, but it's not true everywhere in the universe. Here on Earth, 2.2 pounds a kilo. Okay? So really quickly, let's just kind of say 7.25 kilos, 2.2 pounds a kilo. That's about 60 pounds. Actually, 16 pounds, that's more familiar to us than saying I've got 7.25 kilograms. Even less familiar, $71 newtons of force there, right? 71.1. Now we can always decide later on, like if we were to plot this data, now we're going to have like a data point here, data point here, data point here, no data, and then we have a data point sort of like further down. So we can go ahead and decide, like, you know, we should get a data point. Maybe not to just sort of fill in, you know, sort of our graph with some actual data points, empirical data, just to sort of verify sort of the trend is violated. So we say, you know, a pretty amount of friction here. But if we were to test a point, say, like 5 kilograms, and give, you know, then we would get a frictional force between those two. Right. And as long as we're not like maxed out at 150, somewhere around 150. That's the exactly. Like this 5.0, I think that's a little bit below 5. Like, okay. We might have an intuition about sort of this. But yeah, of course, as we add more weight to it, like it's pushing surfaces together more tightly, right? So we expect it's harder to pull it along. So we have sort of like an intuition about what friction is. We can kind of poorly understand. Question? These are pounds, kilos, 1.5, 2. 4 kilos. 11 point. $11.75. 11.75 kilograms of mass. 11.75 kilograms of mass. Pop quiz on the moon weighs 18.8 newtons less than here on Earth is correct. We follow with it. Okay. I'm tricky there to reinforce the idea that gravity fields local G is local to sort of the object that's creating the gravity field that matters. On the moon, G is 1.6 meters per second squared. So we could say this amount of stuff, right? Like I could take this to the moon and it wouldn't have less weight because I lost it in matter, right? It's the same amount of matter because there's less influence of gravity on that mass. Right? So mass is what's the same. Mass is an intrinsic property of a substance. Intrinsic to how much stuff is made up of it, how much stuff makes it up. G is different everywhere in the universe, different G. Usually we're here on Earth for all the experience we do, so we kind of consider this as constant. A lot of countries around the world, so this kind of use mass way interchangeably. You go to the deli, you buy so many kilograms of does pounds a weight. A lot of other countries use the measure, weight. Kilograms even help. All right. We got 11.75. So on June, when like when it occurred, what we're doing is 102.27. All right. So this surface has like, I don't know, somebody glued these end pieces on here, and there's like a little strip of glue right there. And I can see that as I pull it across. Like the surface is uniform, it's not sort of regular everywhere. I can kind of see when I pull it across there, friction increased a little bit. As you might expect, like you're going over sort of a rougher part of it. Check that again. There's like 22. Right there. Got a table so far. Five kilos. .75 whole kilograms for now. Mental math. Now, while you're at it with your mental math, go ahead and multiply 16.75 times 9.81. Everybody with their mental math knows that it is 0.32. At a point, 30 newtons of fall force. Fire. 10 kilos. 10 kilos. I don't think we're going to get any data. I think we're going to let's go over 26.75. So I did max out our. We're doing science. Test it. That's at 50. Is it more than 50? Because even though the Newton meter is graduated up to 50 Newton, there's space sort of beyond that. So you're saying like, if there really was more than 50, you know, would it extend sort of beyond that? So by taking a little bit of the mass off and just sort of testing like this, max out at 50 here, you know, even less weight, and the fact that it's not going to decrease to 40 or so, it's but just double check this. 26.75 kilograms. Starts out as like 44, 50. That's like 49 now. That's a little bit too precise. In there, it's like more than 50. It's getting worse. Eight. All right, so what happened? Tougher. 24.75. 24.75. On Earth weighs how many newtons?
Teachers, please pardon the interruption, but if you could please take a look at the email from Mr. Fry last night for testing today. Most of them on that list are testing today. Please double check because there are some that are only testing on Thursday. We will be sending anybody that's testing Wednesday to the appropriate room at 9:30. So please go ahead and check that list. Thank you.
46 for that one. Okay. This is the data that we're going to plot, right? The normal force, so this column on the x-axis, and frictional force, y-axis. There's the complete data table. What I kind of want to do with the sandpaper, we could do a full-blown plot, right? We could vary it just like we did, like data. Maybe we could plot it on the same coordinate axes, and we would expect that, you know, the trend in that data would be a steeper line, right? Because there's probably more friction with sandpaper. What I kind of like to do is just look at maybe 2 data points with the sandpaper So like get a value, like let's actually match one of these, okay? And that way we'll be able to go over to the same X coordinate, but we'll plot, you know, that just like two data points. Just, I mean, you can draw a line between 2 points, right? It's not as strong as this, but rather than dedicating sort of the full resources to that, let's just say, let's put 2.25, you know, kilos on here, or, you know, pick a number here. Let's test like 11.75, something like that. Now we can't go too high like we did, because if we already maxed it out wood on wood and we expect it to be more friction, then I'm not going to be able to pull it to the accurate reading, right? So let's actually check this one first, 1.25, and we'll kind of get like a, you know, like a bonus column over here, where we just want the, you know, the normal force and the frictional force, just like two extra sets of coordinates that we can plot, draw a line between them, and just kind of see, like, here's the trend for our wood on wood. Here are two data points we collected for sandpaper. Just to kind of compare this to that, you know, line, even though it's not, you know, as good of a trend line as we'll get with this stuff. So here we'll green chalk for that, and we'll call this a normal force. This is going to be our sandpaper. And so I said, like, here's a suggested data table. You might make, you know, another entry beneath the data table that's like, I kind of ran out of space there, but in your journal, just organize it in a way that makes sense to you so that you can kind of keep track of what we're doing. Like, okay, we're going to take 2 readings with sandpaper now, and we'll just have 2 lines, you know, on our plot. One with all of this data, the trend line, and find the slope, you know, of the vested line, that's mu, right? Y equals mx. Here we'll just be able to compare it with, you know, 2 data points. So we're going to have the same 12.26 newtons of force. Sandpaper data points. So we're just going to have 2 normal forces. Let's do 12.26 and let's try this one. 12.26 and 71.12. All right, let's just check this one first and just make sure we get a good reading. If we do, then we know we'll be able to get one here. So we're going to put 7.25 kilos here. 7.25 to block itself. So there's 7.25 kilograms. Now here you should recognize that we've changed the independent variable. Well, the independent variable is the weight, right? That's the thing we're varying. So we haven't really changed that. Still is the independent variable, but we what the surfaces are testing. A whole separate experiment. It's convenient for us to plot it on the same, you know, coordinate axes that we would make for this lab. Right? I consider this like a separate experiment. Right? You can only vary one independent variable at a time. We're checking something different, right? We're going to get the coefficient of this surface now, always specific to the surfaces. And really the only way that, you know, engineers can publish books, like I could get a book and open up, or you could look up a table of coefficients of find that on these experiments, that's all sorts of different surfaces, publish that so people don't have to do this. We have to figure it out. Again, there's no theory that anyone's come up with that you know, give me any 2 surfaces, and I'll tell you the coefficient of friction between them based on the properties of the surface or something like that. But what, you know, maybe there's a way to do that with like computer simulations or something like that. Like you could scan the surface and look at the actual, you know, all the complexity of the texture there and come up with some kind of equation that would capture this. It's just kind of like poorly understood, and this is the best that we can do. All right, so let's see if we get a reading here. And you can see I'm actually decreasing the mass of my block as I do that, because I can see like wood particles that are off the bottom surface of that as I pull along. We'll consider those those mass losses to be negligible. It's also a little bit more irregular than the wood, like a rip here, and kind of take pieces. And down here, pull this way. If you pull the other way, it'll catch. Let's just check a little time. 37. So here we're getting a frictional force, 37 newtons. Compare that to the 15, and then we have the tested wood. Now we'll just drop it down to the final reading of the day, 1.5 kilos. All right, so for your the fun part, sorry, enough with all that boring data collection. Now we get the fun part. Plotting it down. So scale your y-axis to capture values between, 0. I would include a true 0 because there's not going to be a lot of dead space between like 0 and 2. But if you want to start at 2, you could use that symbol to show you're breaking your graph. So scale the y-axis between, 0 and 50 thereabouts. Your x-axis between, here you might want to break it, start around 10 maybe, and go from 10 to like 250 or 245 or some nice round number like that. Never go up by any odd number besides 5. 5 is an odd number that's okay to go up by because 5, 10, 15, that's easy. That's a nice round scale. So scale the axes reasonably, more than the page. Go ahead and start that analysis right now if you'd like to. Or do something else that you feel to. Right. So that's our lab work for this week. Critical angle. Ever have a chance to look at that? Oh my God. I work with elevate the ramp. There's a lot of them right now. Because if the weight vector goes straight down, there's a component of it that goes down the ramp, and a component of it goes component here is really like this one, I can draw a right triangle right here. And that vector is the x component of the weight. So if it's acting on the object like this, it's easier for me to do my trigonometry if I draw a triangle like that. If you have got an x component of weight opposite this angle theta, this angle is also theta. Now we talked about we've got a 90-degree angle here, theta, minus theta, another 90-degree angle in that has to be theta. With numbers, that's what I use in that video where it's like turning coefficient of friction from critical angle. Let's say 10 degrees is 90, 10, 100. One right here would be all this is 90. Now this is 80, and that's also 10 right 10. Again, just kind of work with that for a little bit. It's like a refresher for your geometry. To help improve yourself, this will always be surpassing it this deeper because it's always that straight down, right? That's just going to sort of open along this. Opposite this angle is the sine of theta times mg x component. That's this component. The normal force that acts normal or perpendicular to the surface, and so the y component of weight m cosine theta because it's adjacent to that angle. 5 is the number just the way. So here we apply the second law, the sum of the forces in the y direction equals mass times acceleration in the y direction. So what will be true when you're going around the rim, the object will not fly off perpendicular to the plane of falling. This direction positive x, but that way positive y. Whatever the angle is, it's up to you as a sort of mathematician doing the analysis. I know math classes are always hard-worded. You know, that's kind of an arbitrary. Let's make this like positive x. That way would be perpendicular to the y-axis. So the axes. All right, so here we have the sum of the forces in the y direction is the normal force. The y component of weight. That equals 0, right? Which is no acceleration. So the normal force equals the y component of weight. And the y component of weight, remember, is mg cosine theta. In the x direction, we have friction opposing the x component of weight. We're considering the point right at the moment when the block against this line on the rim. So they will be equal, but then just a moment later, this is going to sort of, you know, right at that critical angle, the x component of weight, that's going to be the component that makes it slide down the ramp, right? When enough force acts on the ramp, this 90 degrees, right? All of the weight would then act down the ramp, and it's certainly going to fall, right? So there is this, like this is not enough of the, you know, weight would be acting down the ramp. That's too shallow of an angle. There is a point there where enough of the weight will act down the ramp, where it will slide. And that, and just before that moment, the forces were equal. Okay, so we want to consider that point right then. The sum of the forces in the x direction still equal to mass. And so we've got the x component of weight minus the frictional force, 0. And so just at that moment before the critical angle, the x component of weight is equal to the frictional force.
But it is time now for those students that are scheduled to test Algebra 1 or DOC that are on that list that you don't check 15 minutes ago. Please send those students who have in front of you their testing sites. Thank you. And good luck, students.
I wonder if I can edit that on the video later, but then that'll just be part of the. All right. X component of weight equals the frictional force, but the x component of weight we know is this, sine theta times mg. We have mg sine theta, which is the x component of weight, now equal to the frictional force. Remember that the theory that we sort of based our lab work on is that the frictional force equals the coefficient of friction times the normal force. And so here we can substitute this for the frictional force. The weight in the x direction, mg sine theta, equals the coefficient of friction times the normal force. And the normal force, remember, is this, cosine theta. So we can write mg sine theta equals mu times mg cosine theta. And then solving for mu, we get mg sine theta over mg cosine theta. Mass divided by mass is 1, g divided by g is 1 times that is that. And so by canceling these out, we can kind of think, hey, it doesn't matter how massive the object is on the ramp. It doesn't even matter the gravity field we're in. Coefficient of friction, those things don't affect it. Well, what does affect it? The surfaces themselves, how rough or smooth, how sort of bumpy they are. But we can at least get a check of mu. And so there's no way to sort of theoretically calculate it based on an understanding of the surfaces. I can't say, oh, marble has these properties, and therefore its coefficient of friction with wood should be this. But I can say, well, I can work with Newton's laws sort of theoretically and get this sine divided by cosine as the tangent of theta. So I, in my lab, can measure a critical angle with a protractor. I just observe when it starts to slide. That's the moment that I know the x component of weight has mass. match friction, in theory suggests now that the coefficient of friction should be the tangent of that critical angle. And we can compare that conclusion to the one we get by looking for that zip line. Protract. All right, so it's always sort of a debate about where do we measure an under the vertex or protractor right there. Like you believe it to the bottom edge of the protractor. 11 degrees. Come on back over this way. Plenty of time, plenty of time. T equals 60 seconds. Remember, base units in the physics lab, please. A minute. 60 seconds. 6.0 ended up 1, right? All right, there you go. You got the critical angle, you got your lab data, got a fundamental understanding of the universe, you're unstoppable. Good work today, class. That's this. E-learners are dismissed. Have a good rest of your day.